Hello everyone, our project is TicketTailor, a university event management and social engagement platform designed for students, clubs, event organizers, and administrators. The main goal of TicketTailor is to help students discover campus events, join clubs, RSVP to events, receive invitations, approval results, and event update notifications. For club leaders, event organizers, and administrators, the system also provides tools for managing clubs, events, members, approvals, RSVP requests, and notifications. Our final delivery is a separated front-end and back-end web application. The front-end is built with React. The back-end is implemented as a Flask API. And the cloud database uses PostgreSQL. The system is deployed to AWS using Terraform. The main cloud components include CloudFront, Application Load Balancer, ECS Fargate, RDS PostgreSQL, ECR, CloudWatch Logs, and ECS Application Auto-Scaling. Compared with the original proposal, the system developed from a basic event browsing and RSVP platform into a more complete campus club and event management system. We implement club membership, club-only events, event invitations, approval-based RSVP, notifications, calendar exports, and cloud-based security and scalability testing. This demonstration is divided into 4 main parts. First, we will demonstrate the main functional requirements. Then is the non-functional requirements, including scalability, security, availability, and deployability. After that, we will explain the software architecture. Finally, we will summarize the key lessons learned during the project.
I will introduce the functional requirements. Our project TicketTailor is a multi-role social event platform. Therefore, I will use 3 different browser pages and log in with 3 different types of accounts: a normal user, organizer, and a system admin. First, like most websites, you need to create an account and log in before using the system. For privacy reasons, I will not show this process. As a normal user, the first things you can do is go to the event map to look for the event you are interested in. You can use the search function to enter the keyword. If you care about the distance, you can also click on this button to get the permission for the website to access your location. And then choose the distance range. But because we live from the university, so for now you can't say that. Why not create your own event? As a normal user who is not part of any club, you can currently create 2 types of events: one public event for everyone, or a private event where people can only join through your personal invitation. You can click here to select a special fake address and enter the required information. Create the event. Please note that you should not enter any illegal information because the system admin will review what you create. Only the system admin approve your events. Your event will be visible by others. We have built the 2 type of events. Now you can go to your own event management page to check this. And if for the public events, if someone want to join your events, they need to go into the map, find this, and require a join first. So now you will get a notification, and if you want to approve this, just approve it. Now you can find that the member has joined your event. For the private tests, for the private events, people cannot join directly, so you need to invite them yourself. The invited person will receive your message. For now you can say that the invited person can choose to accept or reject it. For now, we can't accept it because you can't enter the 2 events at the same time. So if you have some special request, you can enter here, and we choose decline. Okay, now the users will find this. If you want to join a club-only event, you must first join a club. The type of event will not appear on the public event map. Next, we will let the second user create a club. For example, similarity, if you want to join this club, you need to request first. Then the leader will receive your join request notification and approve your join requests. You will be in the with the select, you will be in the event. Now we will let the club leader, the test 2, create a club only event. After it creates, all the club members will automatically receive a notification, and they can also see the information. If they accept, you can find the event is on your is on your club information. Also, if the event will be starting soon, you also get a notification. Finally, I will introduce the personal profile page. Here, you can edit your profile information. The page also shows the number of events related to you as well as your event calendar. So, if you do not want to log in the website every time to check your schedule, you can click here. You can click here to download to install the calendar. This will add the event information to your system, to your computer calendar.
Next, I will show how the system delivers its important non-functional requirements. We focused on security, availability, deployability, and scalability. For security, we test both HTTP security headers and the backend access control roles. As shown in the screenshot, the deployed API returns security headers such as HSTS, X content type options, X frame options, referral policy, and the permissions policy. We also run automated security tests with PyTest. This test checks tempered tokens, unauthorized admin access, object level access control, mass assessment protection, club approval boundaries, and login rate limiting. The test pass showing that important security rules are enforced by the backend, not just hidden in the front end. For availability and deployability, the backend provides the API v1 health endpoint. It returned 200 OK, and it is also used for load balancer health checks. The system is deployed with Terraform on AWS using CloudFront, ALB, ECS, Fargate, RDS, CloudWatch logs, and auto-scaling policies. This makes the deployment more repeatable and easier to monitor. For scalability, we use K6 tags to simulate public browsing traffic against key endpoints such as health, clubs, and the event map. In the longer normal test, the system handles sustained traffic with all checks passing and no HTTP request failures. This shows that the main public browsing path can remain stable under normal load. We also ran a stateful K6 test, which is closer to real user behavior because it includes workflows such as browsing, RSVP, notifications, and organizer actions. This test completed without interrupt iterations, giving additional evidence that the system supports realistic user workflows. Overall, the results show that TicketTailor delivers its key non-functional requirements reasonably well. Security is supported by backend checks and the security headers. Availability and deployability are supported by Healthy Check, Terraform, and the AWS infrastructure. Scalability is supported by K6 test results, while future improvements could include stronger caching and database query optimization. Now I will explain the software architecture using our C4 diagrams. As shown in the system context diagram, TicketTailor is a web-based event management system for three main roles: students, club leaders, and administrators. The system also connects to several external services: the browser geolocation API, OpenStreetMap, and the calendar applications. As shown in the container diagram, TicketTailor has three main containers. The first one is the React and the White Web application. It provides the user interface for these actions. The second one is the Flask REST API. This backend handles authentication, role checks, and these actions. The front end communicates with this API using REST and JSON under the API v1 path. The third one is application database. In local deployment, the system can use SQLite through SQL Alchemy. In the deployed AWS environment, the same application can connect to PostgreSQL through RDS. As shown in the component diagram, the backend follows a module monolith design. It is deployed as one Flask application, but internally it is separated into these components. This architecture supports the MVP because the front end provides the user workflows, the Flask API handles the business rules, and the database stores precise data. It also supports the key non-functional requirements. For maintainability, the backend is separated into clear modules, so each feature area is easier to understand, test, and modify. For security, access control is enforced in the backend, not only by hiding buttons in the front end, so restricted events and admin actions are checked by the API. For deployability, the separated front end, back end, and database makes the system easy to containerize and deploy to AWS. Finally, for future scalability, the module design gives us a clear upgrade path. If the system becomes larger, high traffic endpoints could use shared caching, notification could move to aggressiveness quiz, and some high load modules could later become separate service. Overall, this architecture is simple enough for the MVP, but still supports maintainability, security, deployability, and future scalability.
Now, I will summarize the key lessons we learned during implementation and the changes we would make in a future version. One important lesson was that the architecture choices should match the project scope. The architecture needs to support the main workflows while still being practical for the team to build and maintain. We learned that choosing architecture is not about using the most complex pattern. It is about selecting a structure that supports the current requirements and still leave room for the future extension. Another lesson was that the architecture should evolve during the implementation. Our initial architecture design gives the team a useful direction. As the implementation continued, some workflows became more detailed and connected. This shows us the need to review the architecture throughout the development. The first design provides the starting point, and the later design decisions need to respond to what the team discovered during implementation. We also learned that the clear boundaries are important in any architecture. Different parts of backend have different responsibilities, so each area needs a clear purpose and understandable interaction with other components. We also learned that workflow actions can create follow-up effects. A single user action may update the main record, trigger the notification. When this still stay in the same request follow, the workflow become harder to maintain and extend. In a future version, we would separate the core workflow updates from the side effects more clearly. The system could publish domain events after the main action succeeds, and the background workers could process the notification and reminders. Another lesson was that the security should be designed across the workflow. We learned the access control and the resource ownership should be part of the design from the beginning. Later, permission design increases the risk and missing important cases. We also learned that automatic testing helps us identify problems earlier, especially in workflows involve different roles, permissions. Automatic tests give us a more consistent way to find the issues before they affect the final demonstration and the deployment. Cloud deployment help us understand how a local application become a delivery system. To deploy the project, the application needs to be packaged and configured and connected with the required cloud services. This includes preparing the containers like Docker, setting the environment variables, connecting the database and also logic services, configuring the routing and managing the infrastructure settings. The benefit of cloud deployment is that the system can be accessed through a stable online endpoint instead of only running on one developer machine. It also makes the system easier to share, test, monitor, and extend. Our future improvement would be handling shared routing containers more carefully. For shared runtime states, we release that the email, the written limit, and the real-time updates may become inconsistent when the background scales to multiple instances. In a future version, we would move these standard containers to distribute infrastructure such as Redis and SQS. For safer future changes, we would use two methods: domain events for workflow changes and version migration for database changes. Domain events would separate follow-up tasks such as notification from the main user action. Version migration such as flex migrates would make database schema changes easy to track and keep consistent with the application code. Finally, we would invest more time in UI components, as stronger product would need clear screens. This is especially important with different roles use the system in different ways. Thank you for listening.